other types of defect are one dimension or line defect, and 2D, or also known as planar defect. In a one dimension defect, it can be defined as generally many atoms in length. Line defect also called dislocation and occur in crystalline materials only. Dislocation are especially important in material science because they help to determine the mechanical strength of materials, and they are two basic types of dislocation. First, we have edge dislocation and screw dislocation. Then we have two-dimension or a planar defect that can be defined as a interface between the adjacent grain in a lattice. Disruption of the long-range stacking sequence can produce two other common types of a crystal defect. First is a stacking fault, and secondly a twin region. So this is how a dislocation look like at atomic level. Here we have a cone, for example. You probably noticed that if you zoom up at this cone, and you can probably notice that they don't have a line up perfectly here, but instead you have this extra kernel above here, far away from the dislocation. The atomic arrangement, it looks normal like a square, but in the vicinity it started to get distorted. The coordination number changes, so as a result it changed the total bonding environment in terms of energy. Because dislocation will cause energy, the region down is under tension here, and where the region at above will be under compression. So we can say that dislocation is a linear or one-dimensional defect of which some of the atoms are misaligned, or in a simpler definition, we can say that dislocation is an area where the atoms are out of position, like what we see in the kernel arrangement of cone in the crystal structure or crystallographic defect. A perfect crystal with every atom of the same type in the correct position does not exist. All the crystals have some defect. Defect will contribute to the mechanical properties of metals. In fact, using the term defect is quite untrue or misnomer, since these features are commonly intentionally used to manipulate the mechanical properties of a material. When we add an alloying element to a metal, it is one of the way for us to introduce a crystal defect to alter the properties of the material. Previously, I have mentioned that there are three basic classes of a crystal defect. First, we have a point defect, which that can be defined as a place where an atom is missing or irregularly placed in the lattice structure. Point defect include lattice vacancies, self-interstitial atoms, substitutional impurity atoms, and also interstitial impurity atoms. And secondly, we have a linear defect, which are groups of atoms in a regular position. Linear defect also known as a dislocation. And the third one, we have a planar defect, which are interfaces between the homogeneous region of the materials. Planar defect include grain boundaries, stacking fault, and also external surfaces. Okay, like what I have mentioned before, dislocation, also called as a line defect, that it involves a large movement of atoms. We call it a line defect due to the reason that they do appear as lines. So these are the collective defect that do not depend only on a single atom. They depend on a number of atoms, and they propagate throughout the material along a different dislocation line. What you can see, for example, in the figure here, is that we can see the dark line that represents the dislocation of the materials. So we can see from the figure here is that the density of the dislocation can be really, really high. So when a stress is applied to a material, dislocation are created in the material. The dislocation moving along intersecting slip planes will interact and they obstruct one another and accumulate. What really interesting about dislocation is that they are not necessarily thermodynamically stable defect. In contrast to point defect, they are introduced through a mechanical behavior. Uh, I think I have mentioned previously that defect will affect many of the properties of the materials, especially the mechanical properties. So here we have different types of dislocation. First, we have edge dislocation and a screw dislocation. Uh, Edge dislocation, it can is a dislocation where the dislocation direction is perpendicular to the Berger vector, and for screw dislocation is where the dislocation direction is parallel to the Berger vector. And there are some materials that have to be extremely pure. For example, materials that are used to fabricate semiconductors, such as silicon, gallium nitride, gallium arsenide. And for these materials to function as semiconductors, they have to be dislocation free. So we see that for some of the examples, dislocation are really beneficial, but for some application, they but for some materials, they are really killing the application. So what you really need to know how and when we need to introduce a defect in materials depending on the type of application.